Thank you, everyone, for joining this Vulkanized webinar, where we will explore cross-vendor mesh shading and source-level shader debugging in Vulkan. The first part of today's agenda will address cross-vendor mesh shading and will be presented by Timur Kristóf of Valve, Ricardo Garcia from Igalia, and Christoph Kubisch from NVIDIA. Then, Jeremy Hayes and Greg Fischer from LunarG will demonstrate source-level shader debugging in Vulkan with Renderdoc. First, a couple of housekeeping items. If you have any questions during the presentation, please ask them using the Q&A feature located on your Zoom toolbar at the bottom of your screen. We are recording this webinar and we'll share the link along with slides when they are available. At the end of the session, please complete the short survey form to help us better design future events. With that, let's get the webinar started with Timur Kristóf from Valve. Timur?
Hey guys, good morning. My name is Timur Kristóf, and I am going to talk about cross-vendor mesh shading.
Perfect.
So first, a brief overview of what I'm going to talk about today. So I'm going to introduce you to the new programming model that mesh shading offers. I'll show you how a mesh shading pipeline looks. I'll talk about some typical uses of mesh shading, and I'll give you some comparison to the traditional vertex tessellation geometry shader pipelines. So first, let's go right into the middle of it. So why do we implement mesh shading? What's the main motivation behind it? The good part is that it gives you a new programming model, and this new programming model enables efficient geometry processing, mostly for scenes that have a very high number of triangles. Unfortunately, because it's different than the pre-existing pipeline, it might be difficult to integrate, and it might be difficult to achieve better performance than the current pipeline already offers. And also, the new API is very low level. This means that it allows you to better utilize the hardware. But this also means that you are exposed to what the hardware requires and how it works internally. And that means you need some vendor-specific tweaks if you want to reach optimum performance. The new programming model is compute-like. That means that mesh shaders operate on a similar principle as compute shaders. And the main difference between the traditional pipeline is that instead of passing through the vertices and primitives from the input, with mesh shading, you basically create your vertices and primitives with an arbitrary topology. And the main thing about it is that it eliminates some fixed function bottlenecks that existed in the traditional pipeline. So with mesh shading, you no longer have to deal with input assembly, and you no longer have to deal with the fixed function tessellator. Unfortunately, this programming model is not suitable for mobile GPUs or tiling GPUs yet. So currently, those GPUs are not supported, or rather, they don't support the new programming model. Okay, so on the basic level, you can use just a mesh shader and you can use just a fragment shader with it. And this pipeline will work, but I would say this is not a recommended configuration. In order to get the best performance out of the new pipeline, I also suggest to use task shaders. This is known as amplification shader, if you're familiar with D3D terminology. So the way this works is that you dispatch some work groups of task shaders, and within the task shaders, you can dispatch some work groups of mesh shaders, and you can pass some optional payload data to them from the task shader. And finally, the mesh shaders feed the rasterizer, and from there, you get a fragment shader which works exactly as it did before. So the two new stages that you get in this new kind of pipeline are the task shader. The primary purpose of the task shader is to determine how many mesh shader workgroups do you need to launch? And additionally, they might have a payload output. Practically, I would say we will always need some payload output, but some effort needs to be taken to minimize this. And the other new stage is, of course, the mesh shader, which uses a compute-like programming model, and it can feed the rasterizer directly. So what are some of the typical use cases for mesh shading? There are two main things that we would like to discuss. So the first, this is called meshlets. This means that when you are building assets for your application, you split or subdivide your geometry into smaller groups of primitives, which are called meshlets. And then you process these meshlets. And the other main use is procedural geometry, which means that you generate geometry on the fly. So you don't need any inputs. You don't need any input assembly. You just specify how many vertices, how many primitives you want to output, and then it's up to you in the shader code to implement whatever you want based on some mathematical formula, maybe. So let's talk a little bit about meshlets, because I think this is the typical, the actual typical use that you are going to see. So when you are building your assets, you would subdivide your models or your meshes into smaller groups. These smaller groups are typically up to 256 vertices and primitives. A more typical number would be 128 vertices and either 128 or 126 primitives, depending on your configuration. And in a typical setup, one mesh shader workgroup processes one meshlet, and one task shader invocation processes also one meshlet. So this is an illustration from NVIDIA about the typical the bunny model and how that is subdivided into meshlets. And you can see that on this example, the model is colored by meshlets. And for how to build meshlets, I recommend you can look into NVIDIA's sample code, because they have a meshlet builder there, which you might be able to use. So we have 3 new dispatch commands. We have the typical direct, indirect, and indirect count versions. These work similarly to how the corresponding draw commands already work in Vulkan. So I'm not going to waste any time explaining them. Let's talk a bit about how task shaders are executed. So typically, one task shader invocation would process one meshlet, maybe more than one, depending on how you want to write your shader. And after this is done, you use a function in the shader, which is called emit mesh tasks ext, which launches mesh shader workgroups. So what I mean by processing one meshlet, I mean that the task shader can determine whether a meshlet is visible or not. So basically if the whole meshlet is invisible, then you don't need to dispatch any mesh shader workgroups for that meshlet. And this is called coarse or cluster culling, and this is very important. And then you get to the mesh shader, and in the mesh shader, typically one shader invocation would process maybe 1 or maybe 2 vertex and primitive. And then the shader would need to use a function called setMeshOutputsExt, which allocates the output arrays where the vertex attributes would go. And only after calling this function is the shader allowed to write to the output arrays. And once again, it's very important that when you write mesh shaders, you follow the driver preferences. So there are several preferences that you can find in the API documentation. I wrote some of the more important ones here, but these are not all. But I think these are the most relevant related to performance. So some drivers will tell you that they prefer that you output compact vertices and primitives. This means that there should be no gaps in the output array. Some implementations will tell you that they would prefer you to index the output arrays using the local invocation index. This is basically the same thing that you have built in compute shaders. And also the implementation will tell you a recommended workgroup size and maximum workgroup size and various limits for both task and mesh shaders. And these limits are something that you need to check. And you don't have to follow the recommendations. It will work if you don't follow them. But we do recommend following them for optimal performance. So the two different vendors, for example, NVIDIA and AMD, they have different preferences. So NVIDIA's preference is that you use smaller workgroups of mesh shaders, and within those smaller workgroups, you would process more vertices and more primitives per each shader invocation. But if you do just that, it will perform horribly on AMD's hardware, because AMD recommends that you use larger workgroups. So by small, I mean like 32 workgroup size. By large, I mean 64, maybe 128. And then on AMD hardware, it's optimal if each invocation only writes one vertex and one primitive per shader invocation. So a good question at this point might be, these are completely opposite. So how do you write a shader which can fulfill both? And the answer to that is we recommend you to write a compile time loop. So basically, you would write a loop which would depend on compile time constants, and you would change the constants based on the driver preferences. And this means that the shader compiler would be able to constant fold them and unroll the loop. So it's not actually a loop that ends up in the final shader. But if you do this, you can write a single source code and you can have that perform well on both of these vendors, even though they have very different preferences. So here is a typical flow of how a mesh shader would work. So first you do some pre-processing of vertex and primitive data. Typically you would determine which vertex and which primitive should the current invocation process. Then you might implement something like per primitive calling if you want. Note that it might not be always beneficial to do this, so always do your research before doing this. After that, you can do some compaction if the driver wants that. And finally, you specify the number of outputs and then process the remaining ones and write the output arrays. So basically, before the compaction, you would process the primitive topology. And after that, you would process the remaining other output attributes. So some typical uses for a task shader is per meshlet culling, level of detail selection, geometry amplification. And it's important to mention that if you have a compute prepass in your application, you can replace that with a task shader and you will get better parallelism. And in the mesh shader, you can do additional fine culling, but that might not always be beneficial depending on your application. So yeah, so basically each task shader can then emit as many mesh shader workgroups as needed. But the benefit of this approach is that if you do coarse culling in your task shader, you don't have to launch any mesh shaders for that particular meshlet, which saves a lot of compute resources in your GPU. And finally, in comparison to the traditional pipeline, I'm just going to reiterate these points really quickly. So mesh shading avoids fixed function bottlenecks in the hardware, such as input assembly and tessellator. It allows you to have more flexible geometry amplification because it doesn't lock you to the tessellation options implemented in the fixed function hardware. So basically, you just achieve amplification by specifying how many mesh shader work groups you want from your task shader. And basically, you can think about the task shader as including a compute prepass in your graphics pipeline. It's not exactly that. It's more efficient than that, but as a mental model, you can think about it like that. And as a consequence, this approach can allow you to pre-compute and discard some geometry early. And therefore, it can also save you bandwidth and computations on triangles which are actually not going to be visible. And of course, the drawbacks is that this is not yet useful on mobile GPUs. It's a very low-level tool. You are going to need to do lots of benchmarking and lots of experimentation to see that you got it right and that you got the performance that you were looking for. Another drawback is because there is no input assembly, there are no vertex inputs. So that means the shader will have to load the inputs in whatever way you want. So this is good for flexibility, but it also introduces some coupling between the data format and the shader code. And of course, you will have to care about vendor-specific preferences. So if you compare a pipeline which has just a vertex and a fragment shader versus a pipeline which has a mesh shader and a fragment shader, you would see that the difference is that in the vertex shader, you don't get any say about your output primitive topology. It will be the same as the input. You can't change it. In the mesh shader, you are explicitly required to specify the topology. So you can change it, but you can also just create anything that you want. And of course, due to how the mesh shaders are organized into workgroups, the programming model is closer to how the hardware actually works. It gets rid of the inputs. And of course, if you are willing to write a task shader, those are more efficient than what you would get by writing a compute prepass with a vertex shader-based pipeline. And here is a quick comparison against geometry shaders. So some people might ask, well, why the hell would I need the new pipeline when I could already do geometry amplification with geometry shaders? And that's a good point. But the thing about geometry shaders is that they are very inefficient on most implementations. I am not aware of any implementation where geometry shaders are actually efficient. And this is because their programming model does not really match any hardware that is currently on the market. So because mesh shaders give you a better opportunity to utilize the hardware, I recommend that if you want to start experimenting with mesh shaders, one of the best things that you could do is replace your geometry shader pipelines with something that has a mesh shader. And finally, comparing tessellation versus task and mesh shaders. The main thing about tessellation is that it's not very flexible and it depends on fixed function hardware. And task shaders are completely programmable, so you could use your own formula and you don't have to rely on whatever the tessellator can give you. So at the end of this mesh shading section, we are going to show you a demo written by NVIDIA. And this demo has lots of primitives, lots of triangles, and lots of draw calls. So it emulates an application which might have similar constraints. But first, please listen to the talk from my colleague Ricardo.
Thank you, Timur. I'm going to share my screen with you. So you should be seeing my slides now.
Looks good.
Thank you. Well, I'm Ricardo from Igalia. I'm going to give you a bit more information about how to use mesh shaders in your application. I'm going to recap some of the points that Timur mentioned. I'm going to fill in some of the gaps, and I'm going also to show you some shader codes, some do's and don'ts of mesh shading. So first of all, first things first, if you want to use mesh shaders in your application, you need to check that the driver and the hardware support the mesh shading extension and probably which features are available. We'll go over the features in the next slide. Then you need to enable the extension and the supported features that you want to use when creating the logical device. And with that, you can start using mesh shading pipelines, which are not a completely new type of pipeline, but a new type of graphics pipeline. You cannot mix the classic and the new shading stages in a single pipeline. Mesh shading pipelines must not include any of the classic pre-rasterization shading stages, but they must include a mesh shading stage. And mesh shading pipelines, as Timur mentioned, have a much smaller number of stages. Now, optionally, but highly recommended for performance, they can also include a task shader. Timur mentioned that very well. And it's worth mentioning that mesh shading pipelines don't have vertex input state. So if you are using graphics pipeline libraries, you don't need to provide that state when linking the final pipeline. And if you are not sure if the systems your users have support mesh shading, you should provide a classic pipeline as a fallback to be able to draw anything, obviously. And finally, to properly use mesh shading, it's recommended that you prepare your geometry assets, dividing them into meshlets, just as Timur mentioned before. This is normally done in advance instead of at runtime. You don't want to stall your application while you subdivide geometry meshlets at runtime. You don't want to pay that price. And this is the features strength for mesh shading that you use when checking which features are available and when creating the device. So the first two features are basically mandatory, are basic and mandatory, and they indicate support for task shaders and mesh shaders. Then there are a few optional features. Multi-view mesh shaders means that you can use multi-view with mesh shading pipelines. That's obvious. Primitive fragment shading rate is a built-in that can be set per primitive in the last shading stage before rasterization. And if the feature is, if this feature is available, you can set it from the mesh shading stage, which would be the last one in the case of using mesh shading. And finally, the mesh shading extension also introduced a few new statistic queries to measure the number of tasks and mesh shader invocations, the number of primitives that were sent to the rasterizer. So if this feature is available, you can use those queries as well. Now, I also wanted to give an overview of how a mesh shader looks like with this YLSL example that serves as a kind of template for a mesh shader. So the first thing you can see is that the shader specifies the local size in 3D, just like a compute shader. And then you can use in the body of your shader compute built-ins like the number of workgroups, the workgroup IDs, local invocation IDs, etc. And also subgroup functions and built-ins if they are supported by the mesh shading stages. But the shader needs to generate geometry for the rasterizer, and it does so following the indexed geometry model. So one array will contain vertex data, and another array will contain indices into the vertex array, forming primitives. You need to specify the type of geometry in advance: points, lines, triangles, and the maximum number of vertices and primitives the workgroup will generate. Mesh shaders may call primitives or do some other kind of initial processing, so the final number may be below the specified maximum, and you need to say how many actual vertices and primitives the workgroup will generate. using the setMesh outputs ext call, as you can see there, and Timur also mentioned before. And after that, the shader can start writing to the output arrays. So apart from built-ins, mesh shaders can also generate custom output attributes that will be input attributes in the fragment shader. In the mesh shader, they form arrays, so you can set different values for each vertex. And a nice addition the extension has is that you can indicate some of those are per primitive instead of per vertex. And in that case, the same decoration needs to be specified in the fragment shader for the interfaces to match between the mesh shader and the fragment shader. Now, I also wanted to show you a task shader, which is also similar to compute. The task shader can pass a payload to the mesh shader workgroups it emits. We mentioned that before. And in the task shader, the payload works like shared memory, while in the mesh shader, the payload is read-only. You cannot write to it. To use the payload in the mesh shader, you have to use just the same declaration as a task shader, and then it becomes available. The task shader will typically do the things that Timur mentioned, like prepare the payload if it uses one, do coarse culling, geometry amplification, LOD selection, all as explained before. And the final instruction is emit mesh tasks ext to launch a number of children mesh shader workgroups. The number is again specified in 3D, and you can vary that and at runtime depending on the culling that you did or whatever. So back to mesh shader, the mesh shading stage. These are the basic built-in arrays for mesh shading. There are arrays of indices first, and the type of data they hold and their names varies depending on the output primitive. And the other two are arrays of vertex data and primitive data. So vertex data includes the typical position and point size, for example, for each vertex, and primitive data includes the primitive ID, layer, viewport, a flag indicating if the primitive should be called or not. I will talk about that a bit more later. And the primitive fragment shading rate that we mentioned before and is blocked by a feature. So the do's and don'ts of mesh shading are based on knowing that, as Timur mentioned, mesh shading is a powerful but kind of lower level tool compared to the classic graphics pipeline. The classic pipeline has been available for many years now, and most vendors have optimized the way it works in great ways. And it may be easy to beat the performance of the classic pipeline in some situations, but in many others, it's not as easy. So you really want to experiment and measure to see if and how to get improved performance. You will not get improved performance just by switching your pipeline from a classic one to the mesh shading one in a simple way. For example, for most applications, if you care about performance but are not using task shaders, you're probably doing something wrong. And finally, as Timur mentioned, you really need to pay attention to the vendor preferences exposed in the mesh shading properties to create mesh shaders that will run optimally for that particular vendor. It may be possible to write those shaders in generic ways that make them easy to adapt, maybe at the startup time, and you should test them, you should measure in different vendors, see what the performance looks like. Related to this is the mesh shading properties structure. Most of these specify limits about the number of workgroups, invocations, or memory sizes in the output, shared memory, and payload. But the last ones that I marked in red here are vendor preferences and are very important for performance. They talk about the preferred workgroup size, if the vendor wants you to access output arrays using just the local invocation index, so they can optimize many things if you do so, or if you should remove unused vertices and primitives from output arrays. In the case of primitives, you can also mark them as called in the built-in arrays, as we saw. And that's it from me. I wanted to mention a couple of extra links that are interesting for mesh shading, and I will give you more information if you want to know more details. First is the Kronos blog post that was recommended reads for this webinar. And the second, a few weeks ago, I gave a talk at XDC 2022 with some basic information about mesh shading. It's an introductory talk that complements the blog post nicely, I think, but it doesn't go as deep as we've gone today. And the last item is a friendly reminder that the Vulkan spec is also available. It contains a lot of details, but at the same time, it should be readable. So if you find something that's not clear or should be improved about the mesh shading specification, you can submit an issue or pull request in GitHub, and that's it. That's all there is from me. Thank you.
Thank you, Ricardo. And Timur, I believe you're going to show a demonstration.
Yes. So I think first, Christoph and myself would like to do maybe a basic walkthrough over the code of the sample app. And after that, we can also show how it runs and what kind of things you can tweak in it. What do you think about that, Christoph?
Sounds great. Oh, and hi from me as well, Kristóf from NVIDIA.
Okay. So I think I'm sharing a browser window right now.
Yeah, looks good.
Okay. So this one, it's a sample which anyone can find in the NV Pro samples folder. It's called the GLVK Meshlet Cutscene, and it's one of NVIDIA's early research projects related to mesh shading. So if you want, Christoph, maybe you can talk a little bit about this, and then maybe we could go over some of the code here.
Yeah, so it's GLVK because NVIDIA also supports the NVIDIA mesh shaders on OpenGL. So the application started out the demo started out supporting both OpenGL and Vulkan. So there's a lot of shared code between the two. The GLSL files are almost the same. There's a few defines in them that trigger different code paths for Vulkan or OpenGL. But fundamentally, they kind of work very similar, but there will be a Vulkan exe generated or an OpenGL exe, depending on your liking. And through the whole CMake thing, if you're just interested in Vulkan, you can also just build the Vulkan version. Yeah, it comes with two sort of cat-like models. One is a sort of a race car that was provided by PTC. And another one is a scanned turbine blade, which is from some university that I just forgot. They both kind of showcase a little bit different scenarios when you run the application. You can switch between the two models, and the race car is basically more like a typical CAD model with lots of parts that like the engine, the various the wheels and so on, while the blade is a single mesh, so one object alone that has a ton of triangles. And so they both kind of stress different scenarios. Yeah, thank you for showing the images here. The demo also showcases the power of the task shader that was mentioned a couple of times now in this presentation, where you can leverage it to reduce the amount of actual work. And in CAD, the typical effect would be clipping planes. And so if you use a traditional vertex and fragment shader pipeline, the clipping plane would be applied after the vertex shader is run. So you kind of would send a ton of geometry that is not even visible in the end. But with the task shader, we can do actually apply the clipping logic in advance, because we have the bounding box for every of these tiny meshlets, and then figure out, oh, it's completely not visible, so let's not render it. In the blade scenario, we have a ton of triangles that are very small on screen. And so the mesh shader allows us also to do some sort of per triangle culling, which is not always beneficial. So I want to make sure that it's you know, as Timur also said, you know, mesh shaders are very low level. And so the API, the benefit of the performance compared to regular vertex and fragment shading might not always be the case. You know, sometimes the old pipeline can actually be faster, or, you know, you have to kind of tweak the values, like the number of vertices, number of triangles that a matchlet has, depending on the usage as well. So it's not the easiest feature. But in this scenario where, you know, the shading is very simple and the per triangle can be beneficial because we have so many triangles that are smaller than a pixel, where you can imagine it's also kind of wasteful to generate all these triangles and then send them to the hardware, while in the mesh shader we can directly figure out, oh, you know, this triangle is actually smaller than a pixel and, you know, below the sampling grid. So let's just not send it to the rasterizer at all. So yeah, there is this potential in the mesh shading pipeline that you more actively reduce the amount of total work that you want to do. And that's where the key benefit comes from. So if you wouldn't do that, then you're missing out on a great opportunity, basically. All right.
Should we show some shader code?
Yeah, maybe let's look at the task shader a little bit, because people might be interested in seeing how this culling is actually sort of implemented. So yeah, let's skip all the beginning and straight go to main. I think this is the mesh shader.
Is it?
Yeah.
Oh yeah, sorry. Yes, this one is the task shader. Yeah. Okay.
Yes. Let's scroll up a little bit that we see the task output. Yeah, thank you. So we can see here we define a struct that is basically the payload that is generated by the task shader, and then you know, becomes the input to the mesh shader. And here we say, you know, to save space, our task shader basically works on a couple of meshlets at a time, which is this NV meshlet per task preprocessor defined. So let's say in our case for NVIDIA, you know, typically we like the number 32 because that's the number of threads in our hardware warps. So we would have, yeah, maybe go down a bit to the struct. Yeah, so we would basically output 32 different meshlets at maximum. I'm just going to stick to the number 32 will vary, and you can actually change it in the demo to see the effect. And as Timur also mentioned, you know, other numbers might work better for other vendors, but for the sake of presentation,
NVIDIA loves 32.
I'm going to stick to that number now. So yeah, so the task shader output is then a base ID, which is basically a multiple of 32, because each task shader workgroup operates on 32 meshlets. And then to save space, we kind of squeeze in the other numbers, which would be 0 to 31, in this delta ID array, just to make the payload as small as possible. And so the idea is that after the task shader is run, the delta IDs would be sort of the relative meshlet that is surviving the culling, so filled from front to back. So the array is if all the 32 meshlets were visible, you know, the array would be filled 0 to 31. But if, you know, if some don't survive the culling, then the array would not be filled completely. And yeah,
this
if we
is
scroll
done to
down,
save on memory space, right?
Yeah, so otherwise you could do UN32 and, you know, just give them all their ideas, but this sort of relative value compared to the base value is to save output space. Yeah, if you scroll down a little bit to the main function, I will just, yeah, so there's a little bit of code that, yeah, that looks good. So we start out, again, some hardware might use multiple subgroups. And in that case, or prefer multiple subgroups. And in that case, we need to use a shared memory variable to figure out the total amount of meshlets we want to emit. If we have just one subgroup, then we can do all the work using the subgroup intrinsics that are available in Vulkan, in GLSL. But if we don't, if we have multiple, then that's the thing that the shader here does. First, it sets the value to 0 for this aggregation variable that we will use later on. Then we figure out, okay, you know, the base ID, so this would be the multiple of 32, where the meshlets start. And then comes this looping that Timur also mentioned. Yeah, because we, you know, typically the loop for us would be just one if we were working on 32 meshlets with a workgroup size of 32. But because in the demo, everything is configurable so that all the various, you know, vendor preferences can be tested, and you can see for yourself what impact it has on performance. That's why the code is a little bit, yeah, sometimes not super easy to read. But yeah, this loop is basically saying how many meshlets we operate on within a thread. So let's assume it's just one. Then we run through.
So you mean the number of iterations is 1, but the number of meshlets is 32.
Yeah, for the whole work group, but one thread is working on one meshlet at a time.
Yes.
So we figure out which meshlet we are operating on with this meshlet local and global. We pre-computed some descriptor for the meshlet, which is the memory lookup we are doing next. And again, the more memory friendly you kind of save your data, the better it is. So in our case, we have most of the information for a meshlet stored in a single 128-bit value, which is a UVec4 here. And within that, we kind of encode a tiny bounding box and so on that we use for culling. I won't go through the actual culling logic, but you can see in the next Boolean where we figure out, yeah, should we actually render this thing or not? And then we start making use of these subgroup intrinsics, where we have a ballot function that basically returns a bit mask for every thread or invocation within the subgroup, which you know, sets the bit for that render state being true. And then we use another intrinsic to compute the number of bits that were set to true, which is the number of meshlets we want to output. Now, again, because of the potential sizing of the workgroup size to have more than one subgroup, we have to do a little bit of atomic using the shared memory to kind of aggregate the output meshlets count. And but if it's not the case, then you know we don't have to run that code. Afterwards, we also want to find out the slot in our output array. So this is the subroot ballot exclusive bit count, which basically finds out what index the bit that is currently set has. And so we can figure out, what is my output slot in the output array for this particular meshlet that we are currently working on. And so if we are visible, then we write ourselves. So our relative ID, the one that is going from 0 to 31 in our current example, in this delta array. And at the end, we have to wait again a little bit for the atomics to sink in and all that. But at the end of the function, you can see that the emit mesh tasks txt is basically then outputting a variable amount of meshlets. Yeah, that's basically how you can do the culling. And you know, the subgroup intrinsics are really a great way to make use of the built-in parallelism, or you know, the lockstep processing that the devices have, because the communication through the subgroup intrinsics is really cheap.
So just a little additional thought here. So we are not going to go into the culling code in detail, but it's an open source sample. So anyone in the audience can take a look at this sample and examine the code for themselves if you guys are interested. I just wanted to say that.
Yeah, and let's show the beginning of the basic mesh shader where we use the payload.
So, yeah, so the sample basically has two kinds of mesh shaders for those of you in the audience who are not aware. So there is one which is called the basic, which implements a pass-through style. So something similar to what you would have already in a vertex shader. And we also have another one, which is more advanced, and this implements per-primitive culling. But I think due to the shortage of time, I think we just show the basic one here, right?
Yeah, and just
okay.
I think most of the general setup is what Igalia had shown already, Ricardo had shown as well. And so we just skip. Yeah, we see, stop here a little bit. If you scroll up to a little bit up. Yeah, here, use task stage. So this shader here supports running without the task shader as well. So that's why there's an preprocessor defined here. Conditional. So yeah, but we see, you know, it's the same struct we had as an output is now becoming our input in the mesh shader. And in the next line,
this is how you get the meshlet ID
exactly
from the delta.
Yeah, from the delta. So we take the base ID from the payload, and then we apply the delta. And the GL workgroup ID X is basically the child index compared to the task shader's output. So in our case, you know, it like the comment says above, you know, it runs from the 0 to, you know, whatever we had emitted as a maximum in the task shader. And because we are just emitting linear workloads here, so we don't make use of the, you know, Y and Z coordinates. It's relatively simple code. But yeah, once we have the ID, then later on we fetch the descriptor, and then we figure out, you know, what meshlet, where to get the meshlet data from, and so on and so on. And yeah, there's a little bit of complexity again, because the culling is also the clipping plane culling, not the triangle culling, but the clipping plane computations are in there as well. But yeah, other than that, you know, if you look at this now, it's pretty much what Ricardo had shown with
so
the loop.
Much of this complexity would not be actually necessary in a normal application. I think these shaders are a bit overcomplicated because they offer a lot of customization options. So I think that
yeah, I think I would
we might have a few minutes to actually show the demo. What do you think about that, or would you prefer to talk a bit more about the shader?
Yeah, just one second. If you scroll down a little bit to the stop here. So one thing about mesh shading is that even though the shaders at first look complex and big, you kind of write a framework once to kind of decode the meshlet, and within that framework, you somewhere call code that is pretty much what you had in your vertex shader. So there is this proc vertex and proc attributes function here, which kind of separate the GL position computation from other attributes like texture coordinates and so on. But if you can think about it this way, then all the complexity about loading your meshlet, finding the vertices that it has, and setting up the triangles, that is code that you only will write once. And then you splice in your classic vertex shading logic. And so you can kind of write it in a way that it's, there's a lot of reuse in code. You don't have to start from zero all the time. That's just what I want to say. And that's it from me on that end.
Okay. Should we show the demo app?
Yeah, I think we have, maybe a little bit of time, and then we can go to the question.
So I'll just need a second to start that. So, is it visible?
Yep, looks good.
Okay, so this one is the race cars scene, and there are in total 9 cars. Right now, only a handful are visible. And these have several, how many million triangles are there? Like 30 million-ish, or I don't remember the exact number.
If you click detail stats, I would assume that, let's hope it works. It calculates how many. Yeah, so 32 million.
Exactly. Yeah. That's okay. That's a lot. So the application actually supports several modes of rendering. So there is the standard Vulkan, which is basically a vertex shader, and that's it. And there is Mesh Shader X, and the application also supports NV, but I'm currently not running on something that supports NV. So I'll just give you the X. And within the application, you get a simple UI, which allows you to configure all the things that we were talking about during the presentations. So this is also something that you wouldn't need to do in a typical application, because what this does here is that it rebuilds the meshlets based on whatever I set in the UI. But I just want to point out that in a typical application, the meshlet size would be something that you determine when you are building your assets. So you wouldn't need to rebuild them in runtime. And so you have several settings here also for specifically for mesh shading, which would, so these influence the preprocessor defines in the shader. And these ones above, they influence the meshlet builder, basically. And we can enable per primitive culling and all kind of other stuff here. I think that's everything that we wanted to show. Christoph, do you have anything to add?
No, sounds good. I think we can go to the QA.
All right. So thanks everyone for listening to our talk about coarse vendor mesh shading. And now is the time for any questions.
So I'm gonna start with the first one. Will hybrid rendering with mesh shader pipeline and vertex or fragment shading pipeline cause additional overhead? So at least on NVIDIA hardware, you can freely switch between the two. I mean, they cannot be in one pipeline, so you will have different pipelines, and you bind your pipeline, make draw calls, and switch between them. So the cost switching is the same as switching shaders. So there's no special cost for NVIDIA, at least.
Yeah, I think it's the same for AMD hardware, that the cost, there is a cost of switching between different pipelines. but I don't think that the cost would be different when you switch between mesh and non-mesh pipelines.
Will there be, so another question is, will there be extra GLSL built-ins to identify exactly the mesh workgroup and triangle and so on that the primitive came from in the fragment shader? No, I don't think so.
Per primitive output for that. There is no built-in.
Yeah.
But you can actually, so the mesh shader allows you to have a primitive ID, which would be an output of the mesh shader. And then you can use that in the fragment shader.
Yeah, so the person is also wondering if they can, so basically you would try to pack as much into the 32 bits that you have from the built-in GL primitive ID and write your own, as Timur just mentioned.
Yeah, you could also use custom outputs per primitive outputs as well. It doesn't have to be the primitive ID.
Okay, another question is more NVIDIA specific. Are there functional losses going from the NVIDIA to the EXT mesh shader? So yes, there are some performance differences, and they actually show in the sample when you switch between the NVIDIA and the EXT when it comes to the per triangle culling, where because the NVIDIA extension allows read and write access all the time to the outputs because they are pre-allocated on that hardware. And so you don't need additional shared memory to do per triangle culling because you can write to the output space of the vertices, read them during the culling, write the outputs and so on. So that has some performance benefits if you need to do if per triangle culling is a win. That said, we try to optimize some of these things in our compilers in the future. But when a vendor extension tends to be always a bit faster sometimes. So
for that vendor.
Yeah, because it is a different functionality that isn't exposed in the EXT, the read-write access. Okay. The next question is, Apple has mesh shaders in their tiling GPUs. While we mentioned here that tiling GPUs don't have them yet. That's what the Chronos. I mean, none of us are vendors for that, so we can't really speak for that.
I think all we can say is you want mesh shaders on your favorite tiling GPU. You can write an email to the vendor of your favorite tiling GPU, and you can make them aware that there is some interest from users. But other than that, I don't think that we can promise anything because neither myself nor the other people here work for those vendors.
Another question, so what scenarios do you expect a mesh-based pipeline to outperform the traditional one? So as was mentioned a couple times, mostly when you leverage things that weren't so easy, like the cluster culling with the task shader, because if you were using compute, then you have to write the outputs of compute, create a draw indirect and so on. And obviously this is still good, but with the task shader, we can keep some of that memory, closer to the hardware or on the chip, and balance between the task and the mesh shading a bit more. And so there are benefits in doing that. As for if you were not using any culling, then it kind of depends on the vendor, the size of the meshlet, the complexity of the number of output attributes you have, like texture coordinates and all that. So I can say for NVIDIA, if the thing is really simple, like in a depth pass or visibility pass scenario, then you should beat the classic pipeline. especially also when you're using 32-bit indices, because then fetching the indices from the mesh shaders is going to be faster than what the built-in hardware does. I mean, obviously, NVIDIA just released new hardware as well, so things change all the time a little bit. So benchmarking best is probably best, but yeah, with the simpler the shaders are, so the less outputs they have, the quicker it will be.
Can I add some thoughts to that?
Yeah, sure.
So the question was, which scenarios are mesh shaders faster, correct?
Yeah.
Okay, so basically, if you have a scene in your app which has a very large number of triangles, then this would be a good way to explore improving your performance with task and mesh shaders. If your application does not have a bottleneck on the amount of geometry that it has, then the mesh shading can still be a good way. It could be some better programming model for your application. So it might be nicer to work with. But if you're just looking at it from a performance perspective, then I think you shouldn't really explore this unless you have a really high detailed geometric scene. And also, speaking of AMD hardware, in this case, you need to use task shaders and you need to use cluster culling in order to get the best performance out of it. So in my experience, cluster culling, if you just do cluster culling and that's it, that is already very nice and that gives you very good performance. But if you don't want to do any kind of culling, then I think the traditional pipeline will be faster on AMD. Because on AMD, the drivers are going to compile per primitive culling in the classical pipeline also.
There is one more thing that we, in a context of streaming data and so on, the meshlets, because you are basically the packing of the vertices and the topology information, so that the triangles, is something that is completely in control of you. Like there are no fixed built-in input, so the input triangles and so on. Everything is up to you as a developer, and so it does allow more compressed representations, and you can use the threads within the work group or the subgroup to sort of do some sort of software decompression and so on that you can't do in a vertex scenario where you only have one thread at a time. So but this is a bit more future looking, where there are potential benefits in having a smaller mesh representation overall. Okay, so yeah, the next question is, good rule of thumb to always align work group size with the subgroup size. Yes, that's definitely true for all the compute-based or compute-like shaders like task, mesh shader, and compute shader. So the meshlet size to 64 primitives, I think Timur already mentioned that AMD probably likes even more, like 128 threads.
Well, I think that their official perf recommendation is like between 64 and 128.
Okay.
But I mean, it's not set in stone. It also depends on what kind of data your application has. The important thing is that you should select a size which fits your data set and which utilizes the hardware in an optimal way.
All right, let's conclude here because we have another presentation coming up. Yeah,
thank you so much. Yeah, great questions, guys. Thank you very much. Next up, we have, got a little lost there. Next up, we have Jeremy Hayes, and Greg from LunarG, who will give us a demonstration of source level shader debugging in Vulkan with Renderdoc. Take it away, guys.
Hopefully you guys can all see my presentation.
Looks great.
My name is Jeremy, and I'm going to be talking about source level shader debugging in Renderdoc for Vulkan. Before I get started, I just need to preface this by saying that this is a culmination of effort from a bunch of different people, not just at LunarG, but also at Valve and at Google and other members of Kronos. There are three main goals to this presentation. The first goal is just to announce kind of formally and officially that high-level shader debugging is now available for Vulkan. The other two goals are to show you how to generate debug information for your SPIR-V. And the final goal is to show you how to use that debug information inside of Renderdoc. So as I said before, my name is Jeremy. There are two Jeremys at LunarG, and people are always getting us confused. I'm Jeremy Hayes, and I've been working with Greg Fischer for the better part of 20 years. With respect to the information in this talk, I've mostly been focused on GL slang. Greg also works on GL slang and DXC and SPIR-V tools. The slides for this talk will be available at the URL at the bottom of the slide. First, we're going to start by talking about an extended instruction set for SPIR-V called non-semantic shader debug info 100. Next, I'll show you how to generate debug information for your SPIR-V. I want to briefly go over some of the instructions inside that SPIR-V just to kind of demystify it. Then I'll talk a little bit about the current development status of all this work. And finally, I'll show you how to use that debug information inside of Renderdoc. So first off, what is non-semantic shader debug info 100? It is an extended instruction set. And anytime you use an extended instruction set, you need to use an extension called SPVKHR non-semantic info. That's at the top of the slide here. Mostly, you're not going to have to worry about this as long as you provide the right arguments to the compiler. However, if you get weird errors complaining about this, you should just be aware of this in case you run into errors. One other thing to note is that if you're targeting if you're targeting SPIR-V 1.6, this op extension instruction is not required. Non-semantic instructions are very unique in that anything that processes SPIR-V with non-semantics can choose to ignore them. Things like drivers probably want to ignore them, but things like Renderdoc choose to consume those instructions so that they can provide a debugging experience. This particular extension, the non-semantic shader debug info 100, was, as my understanding was heavily derived from the OpenCL equivalent, OpenCL debug info 100. Both of these extensions were both spiritually derived from the dwarf debugging standard, which is just a debugging data format that's been around probably for as long as I've been alive and supports languages like C and C++. This particular standard was championed by Balder of Renderdoc fame, so a big thanks to him. So why do we care about these kinds of extensions? The reason is pretty simple. During the compilation process, and particularly during optimization, a lot of information is lost in the core SPIR-V instructions. And this extension simply preserves that information. In fact, if you look at a SPIR-V shader with debug information inside of it, you'll see a lot of redundancy, a lot of redundant instructions. It looks like redundant instructions, but once you do your optimization and compilation, you'll notice that the core instructions are gone. And all that you're left with are these debug information instructions. One last thing to note is that if you're using optimization passes that preserve this debug information, you can debug optimized shaders. And in fact, SPIR-V tools does and should preserve this information. So at the top of the slide, you'll just see an instruction that essentially imports the extended instruction set for this debug information. And it's just something to be aware of in case you see in your shader. Again, if you're using SPIR-V 1.6, this is the only thing you'll see. And the extension itself has a very simple task. It annotates locations, scopes, types, variables, values, and procedures. Both DXC and GL slang currently support this extension. And as I mentioned before, SpearV Tools supports this extension. So that means that you can optimize your shaders and still be able to debug them. At the bottom of this slide, I just have a simple diagram that shows how you can go from high-level source to Renderdoc. If you're coming from HLSL, you can use either DXC or GLSlang. If you choose to use GLSlang, you should just be aware that GLSlang doesn't fully support Shader Model 6. Both of them produce SpearV with debug information embedded. If you choose to use GLSL, you can use GLSlang to produce SpearV. And if you have debug information inside your SpearV, Renderdoc will pick it up automatically. You don't have to do anything special inside Renderdoc. So first, let's talk about DXC. At the top of the slide, there is an example command line that you might use to compile your shader. The important bits are highlighted in orange. The first argument basically explicitly commands the compiler to generate an instruction that imports this extension. It's not required for Vulkan 1.3. It is required for Vulkan 1.2 and older. So just be aware of that. Otherwise, you'll see an error. The most important instruction or argument on this slide is the last one, and it tells the compiler to embed the source string in the debug source instruction. And if you don't do that, Renderdoc will not show you your high-level source. This is how Renderdoc gets the high-level source. And now we'll talk about GLSlang. GLSlang, as I mentioned before, can take HLSL or GLSL. The two command lines at the top should look very similar. The only difference is the -D and the -V. The -D just tells the compiler that the source is HLSL, and the -V tells the compiler that the source is GLSL under Vulkan semantics versus OpenGL semantics. The -GVS command line argument is the most important thing on this slide. It's very similar to the argument we just talked about in DXC. It instructs the compiler to embed the source string in the debug source instruction. If you do not do that, Renderdoc will not work. The last thing I need to mention at the very bottom is that during the development of this extension and for GLSlang, I saw about a 70% increase in size of SpearV for the shaders I was working on. It's just something to be aware of because you probably don't want to ship your debug information embedded in your SpearV. I'll briefly go over what you might expect to see inside the SpearV, just so it's not a mystery. I've categorized this into 5 groups. These are just my classifications. They're not formally defined in the spec. The first is location instructions, things like debug line. And the next is the entire type system is replicated in debug information. So things like scalars, like ints, floats, bools, they're all covered by an instruction called debug type basic. Vectors, matrices, arrays are all straightforward. Structures are a little bit weird. They're covered by a type called debug type composite. Functions are straightforward. Variables, there are 2 variables. There are global variables and local variables. Local variables, just because they have a different lifespan, have 2 additional instructions, debug declare and debug value, and they more or less do exactly what they sound like. Debug declare defines the point of declaration, and debug value represents a changing of the value of the variable. Procedures are straightforward. Scopes, there are 4 basically operands for debug scope. Those scopes are compilation unit scope, function scope, structure scope, and everything else. So things like everything else would be things like anonymous scope and control flow bodies like loops. Let's see. So what is the current state of all this work? Well, we're basically publicly announcing it, I think, with this presentation. So it's ready for people to try. During the development of this extension inside GLSlang, I started with Sasha Williams samples, and I just kind of brute force went through one by one and fixed crashes and fixed validation errors until I had all of the shaders passing. And I've manually gone through a lot of these samples, I'd say a couple dozen inside of Renderdoc, just to make sure that the debugging experience was something that should be expected. Also a huge thanks to Dan Ginsberg, because he reported a lot of bugs and shaders that he saw at Valve. And he also provided those shaders so we could work with him and fix those bugs, which is awesome, because without his shaders, it wouldn't be as mature as it is. Before I forget, I should just mention that both of these, both GLSlang and DXC, we ship GLSlang and DXC that supports all these features in the newest LunarG Vulkan SDK. One final thing to mention is that ray tracing and mesh shading is not currently supported. I don't know what the future is. For those, I know people are interested in them. I just can't speak to it right now. I want to provide a short demo. I'm just going to launch Renderdoc. And before I begin here, I just say that this is not meant to be an introduction to Renderdoc. Hopefully you're all at least somewhat familiar with Renderdoc, but it's pretty straightforward. You start by defining an executable path, a working directory, and command line arguments. I'm just going to load some settings that I had previously saved. We're using one of Sasha's samples here. And we click launch on the right-hand side here. And you should see an application. I'm going to take a capture by pressing F12. And I can hit escape to close that application, and Renderdoc will automatically load the capture. And over here on the left in the event browser, I'm going to choose a color pass and a draw command that I'm familiar with. But obviously in the real world, you're going to choose one that's interesting to you, whether it's a problem or you're just investigating something. And then you choose a pixel by right-clicking. And you press debug in the lower right-hand corner. And if all goes as planned, you should see your high-level source. Before, you would only see something like this, which is just the disassembly. But now, with this extension, you should see something like this. And the debugger controls are all at the top here. You can go forwards and backwards. It's pretty standard stuff, stepping forward, stepping into, setting breakpoints. I'm going to use hotkeys just to speed things up. So if I want to step forward, I can press F10. And if you look in the lower right-hand corner, you should see that frame position got updated. And I can continue stepping along and normal got updated. Just to prove that everything works, I'm going to step along and just go through this loop once. We have a loop down here at the bottom over light count. And I just went back to the beginning of the loop. You can also set things like breakpoints with keys like F9. Also, you can just click on a line. This is what I prefer to do, and then right-click and say run forward to cursor. And if we want to step into the shadow function, we can press F11. So I press F11, and now I'm inside the shadow function, and I can continue debugging. If there's no other breakpoints set, you press F5. It'll execute to the end of the shader. One nice thing about Renderdoc is I let you go backwards, so I can hit Shift F10 and just start stepping backwards through my shader. I can also hit Shift F5, and that'll throw me all the way to the beginning of the shader, or beginning of main. That's pretty much the extent of the fragment shader demo. I want to briefly show you, if I can find, if you click on the mesh viewer tab and select a vertex, you can also debug vertex shaders. So I'll click debug this vertex. And this shader is not very interesting, but it has all the controls and all the debugging support that you had in the fragment shader. One last thing I'll show you as far as debugging shaders, if I can remember how to get to it. Over here in the pipeline state, I'm not going to load an application with a compute shader. However, you can debug compute shaders. You will need a compute pass, and you will need a dispatch command. But you'll need to select it over here in the event browser, and then you'll need to select the compute stage. And this button will be, it won't be grayed out, and you'll be able to press debug, and that way you'll be able to debug a compute shader. That's the extent of the demo. I'm just going to return and finish up the presentation. We have some immediate future work. That immediate future work is squashing bugs. There are some rough edges we're still trying to polish, and there are known bugs, so we're going to work on those first. There are 2 instructions in the extended instruction set that we don't currently support, the details of which aren't really important, but they do enable a feature which some people have been asking for. And that feature is basically allowing us to store the debug information in a separate file from the SpearV, so it doesn't have to be embedded in your SpearV. And I do need to say thanks to all these people, because like I said at the beginning of this presentation, this was a culmination of effort. Big thanks to Dan for real shaders and all the bug reports and testing that he's done for us. Thanks to Balder for the wonderful work he's done in Renderdoc and the extension. Thanks to Sasha for his wonderful shaders, and thanks to Google for all the work they've done in DXC, SpearV tools, and the OpenCL extension. If you have any questions, you can email me directly, or obviously here in a second, you can ask some questions. But One last thing I need to mention is that if you run into bugs and you're using GL slang, go ahead and file those against the GL slang repository. And if you run into bugs using DXC, file that in the DirectX shader compiler repository. Both of those links are here. It's probably best to file it against the compiler instead of Renderdoc. Oftentimes the bugs that Renderdoc finds are not Renderdoc bugs. They're usually compiler bugs. And if for some reason it is a Renderdoc bug, we'll go ahead and forward that on to Balder. One last thing I forgot to mention. The compilers are available through the LunarG Vulkan SDK, but Renderdoc you'll have to get yourself because we don't ship that in the SDK. You're probably okay grabbing the latest stable version of Renderdoc, although we have continued to work on bugs since he released that. So if you run into something kind of buggy, try the latest nightly build, because we have pushed some fixes to the nightly build, or Balder has pushed fixes to the nightly build. One last thing, there is a white paper associated with this information. It's more or less exactly what I just explained in this presentation, and that URL is at the bottom. We can just start with questions now, if everybody's ready.
Sure. Yeah, so far I just got one question here. Does/will GLSLC support shader debugging information? And that's a good question. I guess I'm not quite sure of the status of GLSLC right now relative to this option. So I'm guessing that it doesn't, because we haven't tried it. So I don't want to say it does. It's possible, but I think that I think the answer, at least, it could very well be no at this point.
I guess I'll just say, with respect to the work that most of the work that Greg and I have done, it's in a SPIR-V extension, so there's nothing, I guess, preventing it. It is because it's in the SPIR-V extension.
Right. It's really probably just more of a question of how is it specified on the GLSLC command option, and and whether that's been linked up or not. We just haven't looked at that yet. So we'll write that down, and we'll make sure we'll follow up on that, and we'll make sure that gets taken care of in the next in GLSLC. All right.
So there's another question.
Yeah, I'll. So do other language front ends have to do anything special to have compatibility with shader debugging in Renderdoc? Or will embedding source and adding the appropriate SPIR-V instructions be all that is needed for that work? You want to try that one, Jeremy?
As long as it's a bit complex because Renderdoc does have to support the stage. But if the debug information is available, I think the answer is it should just work. Is that correct, Greg?
Yeah, right. It does depend on support from Renderdoc as well. For instance, we did say that the mesh and the ray tracing is not currently supported, and I think there's more work that has to be done in Renderdoc just to support those stages as well.
Right. And I guess I don't know for sure, but I think with respect to mesh shading and ray tracing, there's probably, I don't know, I'll probably get in trouble for saying this, but I don't think there's a whole lot of effort as far as supporting the SPIR-V.
Well, certainly on the SPIR-V side, there's probably not a lot to be done there, but yeah. All right. Any other questions? All right.
Yeah,
Thanks,
it doesn't
everybody.
look like it doesn't look like there's gonna be any other questions. Thank you, Jeremy, and thank you, Greg. Really appreciate it. As a reminder, a recording of this presentation, along with the slides, will be available on the Kronos Group website, and a direct link will be sent to you in a follow-up email. As you leave the webinar, please take a moment to fill out the survey that pops up. Your feedback is important to us and helps us improve these presentations. Please let us know if there are other Kronos-related topics you may be interested in, and thank you for joining us. We hope you enjoyed the webinar. Have a great day.